Okay, so now what is mutual exclusion? Um, from the traditional operating systems scenario, when you have a resource and you have multiple processes competing to access the resource should be allocated to only one process at a time. So that resource is like a critical section. Only one process can access the resource at any point of time. So we need to kind of regulate or let the processes here to coordinate among themselves, because we don't prefer to have centralized solution. We would look at a centralized solution also, but we want a distributed solution where the processes coordinate among themselves to kind of guarantee mutual exclusion. So we need three requirements to be satisfied when we talk about mutual exclusion. They are the safety, liveness, and fairness. So what we mean by safety, which means more than one process should not get access to the critical section. Okay. So what is liveness? Liveness means the CS request, the CS access request generated by any process is eventually granted. Okay, so no process should basically starve to gain access to the critical section. And fairness means requests are granted in the order in which they are generated. Okay, so if one process made a CS access request and another process made a request after this first process made, then the first process should get the permission to access the critical section first before these other processes given the permission. So that is fairness. So now, in order to do all these things in our distributed algorithms, we need some kind of clocks. So we'll use the physical clocks itself for all these algorithms. Of course, as I said in the beginning or in another module, we can have all these physical clocks loosely synchronized, in the sense that we can say that the time across these clocks will be different from each other at most by a certain upper bound. Then we can say the clocks are kind of loosely synchronized. Okay, and the reason why we need this is we want the timestamps, the messages generated by the processes, to be totally ordered, which means I can say this message was generated either before or after the other message. And if two messages have the same timestamp, then we can order them based on the process that sent the message. So again, the process IDs are unique. So the combination of a message along with its process ID will make the messages to be totally ordered. So we can say which message should follow which message in terms of when you're ordering the messages sequentially. So now, along with the algorithms, we'll also look at the performance with respect to certain metrics. One is a synchronization delay. It's basically the time it takes since the latest process that has exited from the critical section, how long it takes for a new process to get into the critical section. So you would prefer this to be as low as possible, so that critical section is not lying idle, some process is running it. And then of course the execution time of the critical section, how long it takes for a process to after it enter the critical section before it exits from the critical section. So that's execution time of the critical section. And then the response time is after sending out the messages to request for permission to enter the critical section, how long it takes for the process to basically exit out of the critical section. So that includes the time it takes for them to get into the critical section, and then the time they spend executing the critical section. So the time, this includes both. So we call it as response time. Since they sent out the request, how long they basically have to wait, and then how long they took to execute, both put together, the waiting time and execution time put together, we call it as the response time. Okay, so the objectives of the algorithms we are going to see are to minimize the number of messages that we send per CS invocation, which means if I want to access the critical section, I should send out messages to the other processes to let them know about it. So how many such messages the processes have to exchange to coordinate with each other to guarantee mutual exclusion. And then of course we want to minimize the number of such messages. And then the synchronization delay, as I said, is the time between since the process exits the critical section, the other process enters the critical section. We of course want to minimize this. Similarly, the response time, the execution time of the critical section is not under the control of the algorithm. It depends on what the critical section is supposed to do. But the waiting time is a little bit under the control of the algorithm, as we'll see. So you want to minimize response time also. And of course, you want to maximize the system throughput, which is basically how many critical sections you can execute per unit time. Of course, that depends on the execution time of the critical section. So if SD is the synchronization delay and E is the average CS execution time, then the system throughput is 1 over SD plus E.